freezing crack on the copper pipe. So even though this pipe was drawn to increase the strength of the copper, so you use the minimal thickness, there's actually two hoop cracks. What you'll see is there's a bump that was created before the pipe actually opened up. And that bump essentially corresponds to each time you freeze and unfreeze, you get a little gap and you keep growing and growing and growing. So it's a little bit like bursting the pipe slowly by the action of freezing and unfreezing. What I brought as a counterexample is a CPVC pipe, so chlorinated PVC that failed without any deformation. So it's a little counterintuitive. We think of plastic. Well, I guess plastic can behave in so many different ways. In this case, what you see on top, this was a cut made to just open up the pipe, and on the other side, what is more of a rougher surface is a slow crack that started from the inside and went to the outside. These pipes operate typically at 200 psi, so it's a higher pressure here than potable water, which is around 70. So even though it's high pressure, they do use the plastic. One of the reasons is overall cost. It's easy to make these joints using solvent cement, and the piping material is also fairly cheap given the size of it. This specific issue on why it cracked has to do, if you see the little black on the inside of the pipe, there was a little bit of oil, cutting oil probably from other sections of piping in the system that essentially rendered the plastic susceptible to slow cracking or stress corrosion cracking. In terms of the polymers, what I really want to do first is try to discuss a little bit some of the differences. If you remember, so you're going to put the schedule here for next week. I'll be teaching Monday, and then Dr. Jenkins is going to do Tuesday, Wednesday, and Thursday is Mr. Lyons. This week, we have Thursday and Friday left, and that is for Mr. Lyons. I think he's going to tomorrow continue the patent law topic, because that's what was going on last Friday. Okay, so we have, in material selection, we have our objective. And if we're thinking about a plumbing system, a lot of times it will end up being cost. Overall cost, when you include maintenance, of course, you have a lot of constraint. One of them is, the water quality. We could use steel pipe, for example, and there will be situation even with potable water where you're going to use galvanized steel. So you have to make sure that you do meet, however, all to minimize the risk of contamination. We used to have lead in the solder material for making joints on copper pipes, and that was eliminated actually just about 5 or 10 years ago. It was a gradual process. People didn't like the new solders, but eventually it became regulation. You can still have the lead-based solder for industrial application, but nobody's supposed to use it for potable water. What are the other constraints? We don't want it to crack, so I would call it the environmental resistant. And as it turns out, that was the problem here with the CPVC pipe. It was plenty strong to resist burst pressure during lab testing at the beginning, but either they did not anticipate or the plumber didn't know that you had to make sure you don't contaminate the water with essentially a lubricant that will disengage, if you will, the internal structure of the polymer and cause this brittle behavior. We have listed separately. We have time, and this is what's going to be our first topic today with with polymers because time means creep, which is for a pipe, the growth in diameter, the slow growth of diameter over time, and that can lead to crack formation as well. So there's a lot more here. You know, you have a certain, you know, of course you need the strength, but if you define the strength as the short-term strength from laboratory testing, it is typically not a governing criteria in the sense that you can make all plastics strong enough on the short term. What's very difficult, as you'll see, is to make them strong for long-term service under pressure. Not to say they're not used, and we'll go through examples where we actually use them. So one of the issues in terms of the mechanical resistance is what happens over time, as I mentioned here, the creep behavior. So I brought up some basic concept. Most of you may be familiar with creep of materials. This specific curve is actually for metals, so metals will also creep. What I could say for creep here is if the temperature is greater than about half of the melting temperature, is when you can expect having some creep effects. So for lead that we discussed a little bit on Monday, and tin, that could be very close to ambient temperature because of a low melting point. But for steel or even aluminum, you have to elevate the temperature before any of this takes place. With a lot of polymers, I think one maybe exception is PEEK, where there will be some polymers that have a very high melting point. So those will have limited creep at ambient temperature. But most of them, if you put them under load, they will deform. And then the question is how fast is that going to be a problem for the application. So the behavior, it typically has two components, and that's actually very useful when you try to understand what is happening. The transient creep for polymers would be all that viscoelastic behavior. So you put it on the load, and then it deforms pretty quickly, continues to deform quickly, and then it's slowing down. When it's slowing down, it's this transient creep that is stabilizing, but you'll always, with polymers, have some amount of continuation of that flow of the material, the formation of the material, and that comes from the viscous component. So, and the viscous behavior, we'll see later that it's really the macromolecular chains that are moving one with respect to the other, and that's not going to stop. It's a very, very slow rate, and it starts right from when you apply the load. You don't really see it at the beginning. What you see is this transient creep where it's actually big segments of the chains are rotating around themselves to allow each other to move, and you can generate sometimes as much as 10–15% strain through that process. And when you've done with this, now all you can do is really move one chain with respect to the other. It's a slower process, but at that point it becomes time and dependent with respect to the rate. So here it's pretty constant. We talked last time, we spent quite a bit of time going through grains. They have a lot of implications for creep of metals, because I'm trying to do the creep for the two materials here at the same time. And it's a reason why we have single crystal turbine engine blades. We avoid having grain boundaries, which are a mechanism by which you have the creep in metals. There's a lot more freedom at the grain boundary. And therefore you can get more diffusion, you can get grain boundary sliding in very specific situations, and therefore if you have a single grain, now you're forcing all that creep behavior to take place within the crystal, and that's a slower process. So very high temperature application, turbine blades, which we'll discuss later. The most critical application, you end up with single crystals for that reason. Now, there's a little bit too much details here in terms of the different creep behaviors. So let's just say that because I was giving the example of the turbine blade, that it's a big single crystal in the most demanding application, but it has a lot of second phase in it. So if you look at this structure, what it is you have second phase into the matrix. Sometimes it can be up to 50, 60 volume percent, and that is all to slow down the movement of these dislocations we talked about on Monday. So it's a very, very specific case in terms of design, but at the same time, technologically, it's very interesting because all these concepts we talked about come into play here in terms of trying to limit the movement of the dislocation, in this case, to avoid the creep behavior. All right. So we're into the polymer. I'm sure you've heard all these names: polyethylene, PVC, the polystyrene is very common. This is the one that used to be with the bread bag. You have this little plastic thing that you put on to tie it on, and it's got the expiration date. Now we don't really do this anymore, but those little plastic tags, when you bent them, whatever color they had would change to white. And that's the stress whitening, and we'll talk about that here. You have void creation into the material. The reason you do it with polystyrene, for example, is the size of this side group. So here you have a whole benzene group, you have 6 carbon on the side of the main chain. So here's the main chain. So it's a lot more difficult to deform something like this, something like polystyrene, than it is for polyethylene, which is just carbon primary bonds altogether. There is a lot of variation in between those. You can see the PVC is just a chlorine instead of the hydrogen ion. I brought these because they're both clear. Why are they clear? This is plastic. Anybody? Professor Meeker really wants to answer this one. Anybody else? Seriously, why is this plastic clear as opposed to being white, black, or anything else? What makes the light pass through? What is glass? Is glass crystalline or not? It's not. Okay. So that's already giving us a good starting point, right? Because if we think of something that doesn't have a particular orientation, then you don't get all that diffraction and that scattering that's involved when you have crystals. So this what is special here, there's no crystals in these two polymers. Most of them do. So polyethylene, you can't have it transparent. You can try to buy it, but the reason is it will form crystals when it solidifies or when you deform it. So we have here polycarbonate, which everybody knows, I think, from just talking, that it's been used for lenses on glasses, and it's highly deformable. So I'll try to crack it here, and it won't do it on me. It's actually just deforming, it's springing back. If I let it be, it will come back slowly. Now, I've tried this before, so you'll see at the end here what happens when it actually cracks. It necked, so it reduced in size, and you also see some surface features, which we'll discuss later. So let's pass this out, and you can bend it back and forth. This one, try to break it. Oh, I broke this one. Easy. Okay, so there's a difference between them, and it's actually less of a difference than you see. So this is not polycarbonate, this is PMMA. And it was cast very quickly, so it's also amorphous. So the polycarbonate, because of its structure, doesn't really want to crystallize, so it's easy to make it transparent. The PMMA here, a lot of times it will crystallize, and you can see with all these breaks I created that it's not transparent anymore. It's not transparent on the fracture surface, and that is the deformation that took place as I was cracking it. So it's in more places. I didn't anticipate for 2 breaks. So I put these 2 structures here, and perhaps, in all honesty, here is more of by experience, I guess we could probably all agree that polycarbonate, because of all the structure, the benzene on the main chains, that would be hard to crystallize. That you don't have these two small chains that you can align together and make a crystal. That you got, every once in a while, you got a big component, and then you got some small component here with the oxygen. The PMMA is up above there. It also has a double oxygen bond. But I guess that's the idea why it crystallized. But when you have them amorphous, the reason why the PMMA is not as ductile, I can't say for sure. What I would suspect has to do a little bit with the length of those chains. It's very, very rare, so you know, that you'll break a chain of those polymers when you have fracture. A lot of times the chain will either go one way or the other, but it won't break in two. So we call that chain section when it's really, when you have a big chain and say you manage to reach the force to break it right here. That will actually happens more because of exposure to X-ray radiation, not X-ray, just UV radiation from outdoor exposure. That's how you break the chain in smaller pieces as opposed to magnetic deformity. Okay, so I mentioned one special case with these polymers. They were transparent. I think we can all agree that most structural polymers, except polycarbonate, are not transparent. So what it means is they do have crystals. And that's something that actually, for me, as a material engineer, it took me a while to really understand, because they taught me metallurgy more than, you know, polymer science, as I was an undergrad. So I'm going to spend just a little bit of time going through a typical polymer structure and what it means in terms of the deformation behavior. If you cast the polymer, most of the times polyethylene, polycarbonate, and even PVC, nylon is a good example. So polyamide, you'll start forming a crystal at a certain spot in the volume. So what happens in this type of materials is, we haven't talked about metal casting, but metals will tend to form grains from the surface of the mold. But here with the polymer, partially because it's a lower temperature, if I have a certain volume here, I will typically, and there's no specific crystallization temperature, which is very interesting, because of all this organization, there's a need for so much movement of the chains to get together that it will crystallize at different temperature depending on how much time you allow for that crystallization to take place. So if you think of just diffusion for metals as allowing, you have the liquid and all you need is to stack individual atoms. Here you have to stack actual long chains of molecules that have all these side groups. So it's a very slow process. Say it happens at a few locations inside, it will grow from there, and that's what you see here. We could probably, you know, it's up to you with how you think of it, but I like to think of these as my equivalent of the grains for the metal. Because what you'll see is, in terms of the deformation behavior, there is a lot that happens within each of these structures that we call spherulite. And the spherulite have what we call the crystallites, and these are shown here. These are the place where you can probably see the molecules going back and forth, gets folded, and it's very organized. It's a very complex crystal structure. It's not a simple cube like you probably heard for a lot of metals. Now, what's special here is virtually any structural polymer is going to have some amorphous zone, just because it's impossible to organize all these chains and just form crystal. There's going to be some entanglement. There's going to be some chains that are mixed that are not really able to crystallize. So you have a stacking essentially of the crystalline phase, the crystallites here, and then you intermix it with a little layer of amorphous structure. Now, it doesn't always happen that way. If you put nanoparticle, for example, you can change this behavior. Instead of starting from a point, perhaps it's starting from the particle and it's going all around. So, but the gel concept that you can't really organize the entire polymer chains into crystals, it remains the same. So if you're thinking about doing some characterization of what you've produced in terms of polymer, a lot of times you'll heat it up and study, how many crystals did I get. So that will give you the heat generated at the fusion of the crystal tells you how many you had generated during your processing. It has a lot of implication on the properties, and I do want to go through that. You can think of it that if you manage to form more of these, you have smaller spherulites, and it's going to be a different deformation behavior. If you also do it quickly, chances are these crystallites are going to be thinner, and you're going to have more amorphous material. That's going to mean it's going to, not creep as easily. There's so many things that are related to this overall picture. I'm giving you one more example. If I have very long chains, it's harder to form this, right? It's harder to move everything to form crystals. So a very high density, when we talk about density, we mean really the length of the polymer. So a long length polyethylene is harder to make into this crystalline structure than a short length one. Now, let's move into what happens when I start deforming those spherulites. And that is very typical of nylon cord. I didn't bring one, but you all see these yellow cords, or now you can also get it out of polypropylene. So if you take nylon as a strip from casting, a little bit like the one I circulated, it's going to be fairly flexible. It's going to deform. If I pull on it, actually, I'll get, perhaps before I get to here, I'll get 400 or 500% strain. It's going to get much longer, 5 times than it was originally before it breaks. Now, we use that to make polymer cords. So we deform them by about this much, 500-600 times, and we get more of a fibrillar structure where now you don't have this all rounded arrangement. What happens with the rounded arrangement, it doesn't really show here. So let's if I'm round like this, and then I got crystallite oriented in different direction, but if I'm looking at 45 degrees here, I can have 2 crystals. So this is very strong. This is very strong. But in between I have the amorphous material. It's very easy to shear. So if I'm looking at this structure, this is where the permanent or the flow deformation is going to start, because I have that special orientation to allow for it. So that's a little bit how you start the deformation, and as you keep pulling it, you are stretching the chains, and you are aligning the spherulite through that process as well. So you can essentially increase the strain. Doesn't really show here. You can increase the strain by perhaps a factor of 2 or 3 before you get to this very microfibrillar arrangement. That is, of course, if you don't break it. And we'll go to, well, you could probably start thinking, if I'm pulling on this and I'm here, this is the opposite situation. I got 2 crystallite and I got an amorphous material in between. So if I try to pull it, there's going to be a likelihood to start forming voids. So if the plastic deformation starts here, the void formation, if I have craze, if I have stress whitening, it's typically going to happen. So this was the loading direction here. So it's going to happen on the plane here perpendicular to the loading direction. I've got 2 stiff components. I'm trying to open it up, and it's very easy to get an hydrostatic pressure tension there. So, I did have a more detailed view here of how you can start deforming and eventually break down what you had as crystalline structure and turn into the new crystalline structure. It's used, if I'm using an extruded pipe, like the CPVC, the orange pipe we circulated, it went through this process. It was extruded, it was deformed a lot, and it doesn't have that crystalline structure anymore. You don't have to do it intentionally, you can do it through extrusion as well. One of the consequences is the properties are very, very, very different. If we look at that pipe, so we just have a round pipe. The extrusion process, if I have the wall thickness here, is essentially going to create an alignment in this direction. So if I take a coupon here, strip, and I pull it this way, it's going to be stronger than if I go in the transverse direction. And that itself is a big disadvantage, because this direction is the hoop direction going around. So under just the pressure, you have more stresses in this direction than in this one. So you can already probably start thinking, well, how do I know this pipe is going to be good for its application? Because if you quality control test, and that's some of the topics we were talking about in the beginning about testing what you really care for. If you're testing in this direction, or if your process is optimized to create all that texture, all that great alignment, you get a lot of strength here at the expense of the strength in the other direction, the one that you care about. So it's a little unfortunate, but we have to live with it. In terms of the, generally speaking, one advantage of polymers is it's very, very easy to cast into a mold because you don't have to heat it up so much. So if we could, we would make almost virtually everything out of castings. But as you can probably think right now, is if you do that, you will have some spheroids or some kind of as cast structure, and it won't have the properties that you get by deforming it this way. So that's one of the reasons why it's a lot cheaper to cast it. You can make a very intricate shape out of the plastic, but it will typically have limited properties because you don't get all that benefit from arrangement. How it actually deforms. This is tying back to how we started today, saying you're going to have some time-dependent behavior. You're not dealing with individual atoms, now you have chains. So this is the schematic. This outer word is actually for polymers. I recommend it. It's a little bit abstract, but you know what? If you want to really get into the viscoelastic behavior and really understand it, as you did a great job. What roughly it is if you move very quickly, this is applying a deformation, and you idealize the section of polymer as this one big tube. You can stretch the tube a little bit. It's not really stretching. You change its orientation. But then after a certain time, you can start going back to where you were, and the way you do from here to here is by some rotation of the side groups. Because these molecules, if you remember, they are mounted at a certain degree between them. So this one here can rotate around. If this is the axis, it can just rotate around here and make a different conformity. It will change its shape. So this is what leads you to the viscoelastic behavior. You just say, oh, I don't really like this thing. I got too much stress in me, so I'm just going to turn around and go back a little bit to where I want to be. So it's not involving a movement over very large distances. Typically, it's just rotation over the carbon-carbon bonds, or the side groups can also turn. So that's really the basic of the viscoelastic behavior. But if you wait, again, is where you can have the entire length. So if I'm thinking about this one and there's another one going through here, they'll literally move one respect to the other, and that is what I call more the viscous flow. Happens a lot more slowly. So there are a number of models to think in terms of the elasticity and the viscoelasticity behavior. of the polymer. It's really good if you're trying to do curve fitting, but to some extent the curve fitting here is, these models give you logarithmic equation for kinetics, which is really what's happening here, because it's activated. This is thermally activated. So it makes sense that if I take a bunch of springs and that bunch in parallel or in series, I can simulate everything. But it doesn't really tie in as much with what's going on from just this simple schematic between the visco part and the flow part that happens on a longer term. So I find a lot of limitation for this, because most of the times these models assume that you're linear elastic, viscoelastic. What does that mean is, if I take a certain stress, say I'm putting 10 megapascal of load on the polymer, and it's deforming by this much over time, I'm saying if I put 20, it's just going to be twice the amount. Well, in reality, most of the time as you increase the demand, you get a lot more deformation. And that's why it's essentially, it's viscoelastic, but it is non-linear for most cases. It'd be close to linear for polyethylene sometimes when you're very, very close to not moving. But that in itself doesn't mean much. So even though you have this issue of this creep and viscoelastic behavior, we use a lot of polyethylene pipe for natural gas, for example. These are big pipes put underground, and they're supposed to last 25, 30, 50 years. The way you can do it is essentially put a big wall thickness and don't put a whole lot of pressure. So if you can afford essentially putting the extra material to lower that stress, that hoop stress that we were talking about, then you're good for service. And I'll show some curves on how it actually works. The really good thing with polyethylene is it doesn't tend to have a whole lot of issues with the environment. If you have a little bit of impurities, if you have a little bit of oil, it's still going to be fine. It's not like that CPVC which is circulated, which is very sensitive to the environment. PVC is also sensitive. Polycarbonate is not used for these things. It's way too expensive. But if you look into what else could you use, you could use polypropylene, for example. And we go back to a schematic from the beginning. I didn't really mention it specifically, but the polypropylene, instead of, so if I have carbon, instead of having hydrogen on each side, what I do is I replace it for another carbon here. It's hydrogen. So it's essentially a small variation, but it allows to change the behavior. It's stronger because he's got bigger side groups at that point. But the most important part here, especially for polyethylene, is how long these chains are, because if you're going to move one respect to the other, if I make them longer, I'm essentially creating more friction. And this is all thermally activated. So if I make it twice the length, for example, it's going to take a whole lot more time to try to move one with respect to the other because of all that thermal activation in the system. So let's go into more details about how it will potentially break, crack. The first one here is what we called at the beginning the stress whitening. So you created microvoids, and these, by the way, are not all that different from the dimples that we discussed about on Monday for metals, this idea that you create these microvoids when you're deforming. What is really unique here is just like you form the nylon cords by this drawing process and making them much stronger, the fibrils here in that craves do the same thing. They're still connected on each side, and they still hold the crack-like feature together, the craves together. So this is still carrying load, as opposed to being a crack like you'll have at that point on a metal. So no instantaneous break if you form these crazes, and it can be pretty big. I had some samples. If I'm looking here at the pipe and I blow this up, I've tested some samples, so this would be 2 millimeters. And I'll form a big craze here in the middle. It almost covers half the thickness. And it's still holding 60–70% of the break load. Is it always going to hold it? No, because if I still keep the load, that craze is going to continue to grow. For the same reason that you have creep in these materials. So at the very, very edges of these crazes, the material over time gets the opportunity to slide, and essentially you separate the micromolecule as opposed to breaking them. And that's how the creep really takes place here. The reason I emphasize this, and it's written on the slide, is if I have longer chains, sometimes maybe it's not going to be as strong when I pull on it because I don't have as many crystallites, for example. It's a different arrangement, so it may look softer if I do a pull test. But if there's a craze in it, it's not going to propagate, it's not going to be growing as easily because I can't separate these chains. They're just much longer. This is a little bit how it can look like on the surface of the sample. So you see this very light. It's not the best viewing here, but you see the surface. It's a surface, so we're not looking into the bulk, and that's why these edges may look a little more square than they really are. On the blow up here, you can see you're applying the stress in this direction, and it's starting to form the craze between those crystallites that we talked about at the beginning. So there's a lot of implication associated with the original structure here and forming the craze. A little bit more in details here on how the craze can grow. Again, it is not by section of each chain. It's one chain is going to have to go on one side or the other side of the cracked front. And that's a slow process, but it can be pretty quick if you don't have a lot of molecular weight. So if I'm thinking of chains that are, if this is, say, 50 micrometers, and that's the overall span of where the molecule is going, it can move around very quickly. But if the chain is very long, then you don't have that problem. Now, I'm talking about all this, but maybe I should have said at the beginning, we talked about thermoplastics. So here we don't have these cross links that are preventing the movements between chains. If I'm talking about epoxy, for example, that'd be a different behavior because I can't move between the chains. I cross-tie them together. So this is a special case for thermoplastic. The example of the polycarbonate, the one I circulated where I said there's a little bit of a surface waviness, is likely to be related to this other mode of localized deformation. Because what happens with the craze is instead of deforming through the entire material, you have a lot of strain that's over a very, very small thickness into the material. But you can have that here, what we call shear bending. It's not exactly as common. It's how deformation starts. If I'm pulling on a sphere-like, right, it's going to localize on one plane. But what's happening here, this is most typical in polycarbonate. Well, that's how you get the view into it. It's transparent, and then you start forming these localized zones here as you're moving forward. So the crack is from here, and it's going that way. And at the very tip of the crack, instead of deforming the whole zone, you're deforming at angles. And I think the main way I think of this is this will happen if you don't form voids very easily in the material. So if you're not forming crazes, you'll shear. These are the two main options for deforming. Now, the question of whether you're going to craze or form the shear bend, I didn't go through the details. I'm going to do that a little bit next Monday. But it relates to the glass transition temperature of that polymer. Essentially, if you have a polymer that can move easily, like polyethylene, that is a very low glass transition temperature, it's got a lot of free volume into it, it's not that far from melting, then it would be very easy for that polymer to form the shear process as opposed to starting forming voids right away. If I have the opposite case, like polystyrene, is where it's so hard to start moving, I have already very little free volume in my material that I'm going to start forming these voids very easily. So the glass, what we call the glass transition temperature for those two examples, for polyethylene, it'd be less than 0 degrees Celsius. And then you're looking at polystyrene around 70 degrees centigrade, something like that. So you can rate the materials a little bit that way. The 0 is actually polypropylene, so polyethylene is a lot colder than that. And that's a little bit how you can, if you know the glass transition temperature of a polymer, you can already get an idea of how it's going to deform. But that's a little bit, we'll get back to this in more detail so you have a better feeling. So I said we'll use polyethylene a lot for pipes. And I talked about how we're going to reduce the loading. And these curves essentially just give you some idea that if your burst stress when you do a test in the lab is of the order of 17 megapascal, you're looking, depending on the temperature you're at, you're looking at failing somewhere of the order of 5. So you get a big factor here in this service life. And that's going to depend on your temperature. If you say the pipe may be at a higher temperature, now all of a sudden if you start at 17, you're looking at 4 megapascal for your strength down the road. So these are very, very low values, but we will design for them. So one way is to take it as a sequence model, is to just say, you know what, after a certain amount of years, this is how much stress is going to be in there, so I'm going to keep it that way. But if for steel, we say just basic structural steel, if you use a pipe, say you'll be allowed to 150 megapascal, for example, something like that, for just a basic structural steel for actual surface stress. Well, here you are in the 2 to 3 range, so it's a lot lower. But hey, if you don't need a lot of pressure, if it's the gas that you're circulating, you don't need a whole lot of pressure differential to circulate the gas, so that will be probably okay. You just put in a pumping station to keep flowing the gas. So there's very specific techniques if you're going to go and actually design for the polymer to be used in long term. But the main item here is lowering the capacity and not relying at all on the result from just a tensile test in the lab. These are all tests that keep track of how the specimen elongates over time. That's what dictates this design here. So one example of the effect of the molecular weight here on the polyethylene. We're talking about a weight variation of 1 order of magnitude here. And if, say, we have a stress of 15 megapascal, just for our example, we're switching from 10 to the 4 cycle to failure. This is fatigue. We use fatigue a lot, cyclic loading, to accelerate what will happen under constant load. So you're going from 10 to the 4 to 2 or 3 times 10 to the 6, just by increasing the molecular weight. So that's a real effect, and that's why there's a difference between low density and high density polyethylene. So the high density is the one that has the longer chains. This is, I guess, an example that I really like showing for why you don't want to rely on on this tensile test to predict the strength of the material. And I'm going to be looking in a practical range of molecular weight, say from here to here. So there's going to be a certain range of molecular weight where you see that the strength is higher, and that's because you form more of these ferrites, and they have a lot more crystals, so you're increasing your short-term strength than if you have higher molecular weight. But it doesn't, we know from everything we've talked about today that you're going to have a lot more creep resistance and fatigue resistance, long-term resistance with these long molecular chains. So it's not a valid test, essentially, to do the tensile test to look at those polymers. What becomes one of the basic requirements for the resin is they do a viscosity test before they make the product. So it's a very standard way to heat it up, and they look at how easy it is to flow the resin to determine, to have some qualitative value for the molecular weight. Molecular weight is very, very difficult to measure directly. So for quality control, they have to do that. And then as part of the design, they have to do up to 10,000 hours of creep tests at different temperatures to know what will happen. So that would be, say, 4 months of testing to be able to say for 25 years, 50 years, I'm going to be able to have the life that I'm looking for. So we've covered a lot of different topics. And I'm happy to discuss any of these in more details. The very first one was the structure of the polymer. That, of course, for those ferrites and all that, it's very different than the metals that we talked about that were grains. But when you go to the bottom of it, it's very useful, because just the idea that when you start deforming it, instead of being these round sphere, you can align it, now it's stronger. Gives you some idea of what's going on with the internal structure of the material as you process it or during application. And I hope we all agree here today that if we can control the length of these chains of polymers, we are much better able to know what's going to happen long term. Because eventually, if it's going to crack, if it's going to form a craze or anything, if it's going to flow, it's going to require the movement between these chains, and you reduce it by making the chains much longer. If you have the craze, that was the case, as I said, it's not a crack because it's still carrying the load, and the stability of those crazes is very, very dependent on the molecular weight. The glass transition temperature, I've discussed about it a little bit today, but we'll take that up in a lot more details on Monday. It's very useful, but it brings on a lot of different ways to measure it, different ways to think about it. It's essentially one way where we can accelerate testing. Some people will do a 1-week test to get some idea what would happen after 50 years by referring to that glass transition temperature. So it's the time temperature equivalence. So that was really a lecture. I didn't get you guys to participate a whole lot. Any questions? Anything to discuss? You were all awake though. Thank you.